super excited to have Yejin Choi visit us today. Yejin has been one of my favorite researchers in the past few years, working on, I mean, really, every time I hear her speak, I feel like I learn not just some new result, but like a new way of thinking, which I think there are few speakers that I can say that about. So Yejin has been working on human language in general and systems for understanding and processing human language and machine learning more generally. And I'm not the only person that thinks so highly of Yejin's work. Her work has been recognized in like numerous best paper awards and all the conferences you can imagine, including both natural language conferences and AAAI, ICML, NeurIPS, but also, and I think this speaks to her breadth, not just in NLP, but also in computer vision, where she got the MAR Prize and the Test of Time Award, and then in robotics, and award in Robocop. Computer vision, but in
that's
robot.
something else. Okay.
Okay, she'll excuse later why actually. And I think this speaks both to work and also what I appreciate about the work is the pragmatism and really trying to see, understand things from a very broad perspective. And so considering all this, it's not surprising at all that last year she was awarded with the MacArthur Fellowship that really I think recognizes this not just quality of work, but also this wide breadth. So today we're very happy to have Yejin here, and she'll be here also for the rest of the day and talking to us about possibilities and impossibilities, I assume, in large language models.
Yeah, what else?
I don't know. Okay, thanks, Yejin.
Okay, yeah, thank you so much for being here. I'm always very excited to revisit TTIC every few years. Just to set the expectation right, there are a theoretical undertone to the questions that I'm going to raise in this talk today, but the answers are by and large empirical and best effort based, so no clear conclusion. If anything, it's likely that I'm going to raise more questions than what I'm able to answer in this talk. So if you feel at the end of this talk way more confused and you feel like you know less, then my mission is accomplished. So I used to work on common sense, or best known for working on common sense, which I began about 6 years ago when people told me that don't work on it because it's a research topic of 70s and 80s and shouldn't work on it because it will never work, and in fact don't even say the word to be taken seriously. But I managed to get tenure at UW regardless. Fast forward this year, people tell me entirely opposite question now, that NLP, common sense, whatever you put in the ... is almost already solved by ChatGPT. So what are you gonna do next? They ask me, or that they have a existential crisis. So it might be that this is a hasty generalization fallacy, a case of that. And let me tell you a story. In late 19th century, there was a student, Max Planck, who wanted to do PhD in physics and asked Professor Philip von Joly about that. And basically, professor said, go do something else because, it's almost solved. So Max, the student, said, I don't want to discover anything new. I just want to understand the sum. And then he went ahead and created this entire new field of quantum physics. So it's possible that we actually don't know as much as we think we know about intelligence, whether in the artificial form or in a natural human form. And there's a lot of this sentiment around both inside and outside of AI field right now that things are just around the corner. We got this. We almost figured this out. And I do wonder whether that's true or not. I actually don't really know genuinely. I have a speculation biased more toward one direction than the other, but I don't know. So let's find out. So this paper to appear at NeurIPS this year, by the way, it so happens that the first 5 co-authors are all women, which I don't think ever happened in the AI history. So let me know if you know other paper of this nature at NeurIPS or elsewhere. This was not planned. It just happened. But anyway, so I hear that, by the way, you already read this paper in the seminar, so I'm going to go super fast, but give you a bit of a story.
I don't know who you heard that from, but it's only a small number of people.
Yeah, but in any case, I'll give you still probably new story angle that you may or may have not seen by reading it. So, in this talk, I'm going to focus on multiplication. So you ask 3 by 3 digit number multiplication, GPT-4 says something, sounds kind of correct, except it's not. But you heard that you have to ask, think step by step. Then it generates this trace of multiplication that looks correct. And also the results are now different. So maybe this is correct, you might wonder, except it's not. So it turns out if you ask these questions systematically over different kinds of 3 by 3 digit multiplication to just GPT-4, then it's about 60% good. And if you stop here, you might come away with this idea that, oh, it's about 60% good. But if you do 4 by 4 digit, it's a 4% good and 0% for the next digit up. Okay, so when I saw these results, or even before seeing this result, I tried to predict what I think GPT-4 is capable of or not. And I found that it's very difficult to predict correctly. So if you haven't seen the paper, let's try to predict with me. But before going that, let me justify why on the earth multiplication in 2023 when we're supposed to work on something much better. That's because it's an easier way for us to study computational cases. And in the paper, we also look at dynamic programming problems as well as Einstein puzzle. But yeah, even I never thought that I would write a paper about multiplication this year. But regardless, some people liked it. Like Kevin Murphy liked it enough to tweet about our paper. And then some other people tweeting about it as potential reduction on hype, basically. So the next question we had was, okay, maybe GPT-4 didn't see a whole lot of multiplication examples. So what if we do supervised training? So what do you think GPT-3 Da Vinci is capable of? The max size, which is 175 billion parameter model, when you give 80% of 1.8 million examples, that's a lot of examples. And why 1.8 million? Because if you enumerate 1 by 1 digit, 2 by 1, 2 by 2, 3 by 1, etc., up until 4 by 2, then that's about 1.8 million, which we divide into 80%, 10%, 10% for training dev test. So what do you think? This is easy enough for GPT-3 supervised training or not? So I thought this should be possible, but GPT-3 achieved about 55% accuracy. So at this point, we thought maybe this is tokenization problem, because the way the tokenization works is that some numbers are jumbled up together as one token. But we cannot train something of GPT-3 scale from scratch. I just don't have that kind of compute. And we used basically the API button on OpenAI GPT-3, where you pay and they do fine-tuning, whatever that means. It's opaque. But that's what we did for supervised training. But as far as training from scratch with different tokenization, the only thing we could do at that time was GPT-2 max size. So that's 1.5 billion parameter model. But on the other hand, we can do only 10 tokens, 0, 1, 2, 3, 4, etc. So that seems very easy, no? This seems like with this many examples, with that little token, GPT-2 with that many parameters should train, wouldn't you think? But it's actually even worse. So it was doing only about 10% good, to the extent that we were able to train. And I don't know if there's some other way of training it so that training does take off, but this was our best effort. So weirdly enough, tokenization was less of an issue, and it's a good thing that pre-trained model was used instead, which again, I don't have answer as to why that may be the case, but actually prior work reported some similar observations, so it's not entirely surprising either. But anywho, some of you might wonder, hang on a second, even humans cannot do this in one shot. We have to have a scratchy pad so that you can do multiplication by step. So we did try that with the GPT-4 by giving these sort of examples explained in natural language. And we did the best we could at that time. In fact, other people also designed the scratch pad. Actually, Google researchers designed the scratch pad for their paper that I'm going to mention in a bit. We used that as well, and we improved it further. So this was our best effort at the time. And we were able to achieve about 92% accuracy by doing so with GPT-4. Now, that's a big jump from what we had before. But note that it's not 100%. So that's interesting. But it's really impressive how the scratch pad is fairly complex and GPT-4 is capable of understanding it and then corrects about 92% of the time for 3-digit multiplication. But again, if you stop there, you come away with this impression that, oh, it's almost there, almost. But if you do 4x4, even with the scratch pad, then it doesn't work very well. It's like we're scratching our head, like, what's going on here? So yeah, lots of I felt like lots of roller coaster riding where I cannot tell what the future up and down is. But anyway, so when we had this paper out, there was one Twitter message we saw, which is like, hey, transformers absolutely can learn true multi-step algorithms in context based on that paper from Google and generalize to arbitrary problem sizes. Can you explain, why our paper says otherwise? So the problem these days with Twitter is that, or I should say X, is that nobody reads the papers and they just look at their tweet posts. So actually open the paper, please, because if you open the paper, that paper said subtraction works 65% good and multiplication works about 80% good. Like, you wouldn't be amazed by my performance if I tell you that I can do subtraction about 65% of the time. So this is, I would say, partial mastery, not full mastery. And in fact, you might wonder, why is multiplication actually better than subtraction? So you have to really read the paper to see the details. But basically, the authors also say that beyond the 3-digit, for some reason, GPT-4 is not very good. So for any longer digit multiplication, they manually reduce it down to smaller digit multiplication and then sum them up. That's a lot of help, right? So, I would say actually what they did, what we do, it's the same results, but, the goal of the research was entirely different in the sense that they wanted to see whether they can improve very poor performance to reasonable, much better performance, versus we wanted to see, can we actually push it all the way to 100% or not? Because GPT-4 seems so magical, transformers seem so magical, is there any limit? We just wanted to see whether we can push it all the way up, and we found that it's actually surprisingly harder than we would have expected. Okay, so one more thing, because some people still want to know, like, oh, maybe supervised training works, so train with the scratch pad. So here's the price range we're looking at. So if we were to do 5x5 digit all the way, it takes us only $700 million that I don't have. Yeah, what a waste of money. So we did something smaller, just to get a sense of, if you supervise the train on GPT-3 Da Vinci model with the scratch pad, does it really generalize better for out-of-domain? So the answer is, it does really well for in-domain distribution, but still unseen problems, but in-domain in the sense that the problem size is similar. Whereas if you add one more digit, then the performance drops down to 0 very quickly. So that's not very satisfactory. After we posted this on archive, we also looked at, what about grokking? Maybe some people worry that we didn't train it long enough. If you trained it even longer, magic would have happened. So, of course, there's a limit as to how much you can do this. So especially sitting in academia / nonprofit research institute. But compared to other prior research that studied grokking and comparing the step size of those papers versus the step sizes that we did, it seems to us that we tried reasonably hard enough. Again, if you want to try it fully, if you have funding, go for it. But this is our best effort. Okay, so the conclusion is that the performance is not very satisfactory, but sometimes it's working really well. So we wanted to then understand when does it work versus not working. So we thought about this computation graph, at least from human perspective. When you multiply 49 with 7, you kind of need to do this like step-by-step multiplication, interleaved with additions, and then remember to carry things over. And so you could trace this to a computation graph. By the way, I understand that you can do multiplication in many different ways, so this is one version of it. And at least this goes along with the Scratchpad that we are using. And we found that there's interesting correlation between the graph complexity of a particular problem instance and their likely performance. So again, this is not entirely predictive. It's correlation. But we found that in general, if computation graph is bigger than or more complex, then the performance is likely less. But as a thought experiment, if I ask you multiply 1,000 by 5,000, you actually don't need computation graph per se. You can just copy and paste, right? So we found GPT-4 does exactly that. So for those cases, it doesn't need to do multi-step reasoning. And we found, in some sense, whenever a subgraph repeated so many times in the training data due to that portion of computation appearing in many different problem instances, then that portion tends to be correct in the test scenarios. So it's almost as if some of this multi-step computation got collapsed down to one step, memorized retrieval of memorized results of that portion of computation. So we have some quote unquote theory like flavor where naturally the more complex it is, the performance will decrease, which is pretty obvious, but it's in the appendix. But I wanted to mention that there are actually, we're not the only one. There are many papers, I don't think I'm exhaustive here, which is that shortcut learning in deep neural networks, or transformers learn shortcuts to automatas, or some such papers prior to our paper. But the reason why we felt that we needed to write this paper is because these papers were experimented with GPT-2 scale, or even less. And there was a bit of a sentiment in the community that magic arises when you go to GPT-3 and 4 scale. So, some of these analysis about shortcut might be irrelevant is some of the sentiment that we noticed in the research community. So we wanted to see whether that's really true or not. And what we find is that there's some shortcut matching still going on, regardless whether, the models are multiple orders of magnitude larger compared to GPT-2 and below. It's 2 to 3 orders of magnitude differences. So at this point, some of you might wonder, hey, why do you even try to do multiplication? That just doesn't make sense. So that's precisely our point that I'm going to come back later when I talk about common sense. But for now, just bear with me that, tool formers, the tool use, the sort of approaches that call calculators and all seems to be more sensible things to do if we're going to build on top of current way of doing transformers. But part of me wonder, is there really fundamental differences between some aspects of multiplication versus some other common sense problems that I will show you later in the talk? I mean, it's a very different problems, but I do see some vague analogy there is what I'm trying to say. Again, like another possible question is like, the multiplication seems to be just like weird edge case that we shouldn't care about, and otherwise, this pre-trained transformers followed by RLHF seems to be everything there is. So I kind of wish maybe some theoreticians can answer this question, like how much is feasible, possible, or not possible under current paradigm. But okay, so I don't do theory research, but let me highlight some theoretical work in this space. So Ashish is my colleague at AI2, and then William Merrill is a PhD student at New York University, who looked at some provable limits of what transformers can and cannot do. And so this paper is TACO paper this year, and that paper just got accepted to NeurIPS this year. And so what they do is something like this. So they show that encoder-only or decoder-only transformers can do only TC0 at most, which means it cannot do a lot of seemingly simple polynomial time algorithms or problems such as home satisfaction problems or graph connectivity or linear inequalities, let alone NP-hard problems as planning. But and also arithmetic, they don't know for sure because their bound is not tight in their own words. But with chain of thought reasoning, they've been working on the fact that you can actually go much further up. So maybe everything under the P categories are possible. So this is a new archive paper. You can look it up. It's out 5 days ago. That looks at the expressive power of transformers with the chain of thought. So still planning is out of this scope, which also makes sense because GPT-4 paper as well as other papers reported that planning is particularly hard for GPT-4. Right, so that's the possible impossibility segment of this talk. But maybe it's a little bit like too negative, and why are you giving hard time to my precious GPT-4? So let me give you entirely the opposite angle of let's make something possible, even though it looked so impossible. And so this is an interesting conversation this year. Someone asked, Rajan asked Sam Altman, how can Indian startups create foundation models for India? And Sam said, it's hopeless to compete with OpenAI. Don't even bother, he said. Although this conversation happened in India, it could have happened in Korea or in any universities for that matter, right? It kind of looks hopeless without compute. Where a lot of engineers working on this shared one goal. I hope that, by the way, Indian startups don't give up. So. Here comes impossible distillation, where we wanted to see whether we can do something crazy. By the way, the second author, Peter West, is on the job market. So the winning recipe right now appears to be that A, extreme scale pre-training, B, RLHF at scale, right? This is the winning recipe. So in comparison, we wanted to test the following scenario. Start with the GPT-2. You remember GPT-2 that nobody talks about anymore? That's so bad, low quality, small model. And then somehow, I don't know how, somehow make a high quality small model such that we're going to compete against GPT-3 for a task. Okay, I'm not going to compete against GPT-3 for everything, but for a task. There are 2 orders of magnitude differences in the model size, so this just seems like impossible. Especially when you see, tweeters talking about papers like this, which says the false promise of imitating proprietary LLMs. And, basically they say, well, it's kind of hopeless trying to distill out of larger models because the smaller models are just not as good as larger models, period. So let me give you a little bit more nuanced description around that. So what they report is true for the experiments they did do, especially focusing on natural QA, that requires more knowledge-based QA, in which case larger models do have a lot more knowledge. And you cannot just distill that like a vast amount of knowledge by creating some QA problems out of large models. So what they found is true for their experiments, but it's not true that small models are all completely out of league, because there are many papers, including our own, that reported task-specific distillation does work. And here I'm not talking about the classical notion of distillation that is by and large about compressing the model size, but what I like to call as a symbolic knowledge distillation, which means you distill some data set out of larger models and then try to do things that focus on, for example, a common sense model or some sort of like confined reasoning problems or even chain of thought reasoning that's not supposed to be not emergent in smaller models, but you can make it more emergent or more like imbued into the smaller models if you distill that capabilities from larger models. So there were a lot of work like this already. And in our work, though, we wanted to get rid of larger teacher model. And for a particular task, we decided to think about how can we learn to abstract? Because it's just a problem that's been bugging me forever, especially that larger transformers tend to store the entirety of the long context as is, whereas us humans, we have very small working memory. So the fact that it has larger working memory is not necessarily prerequisite of gaining really strong intelligence, but it might even be a bottleneck to acquiring certain kinds of intelligence capability. So anyway, so long story short, we wanted to work on abstract, but as a rough approximation, as a starting point, we're going to look at sentence summarization problem. So okay, recap. What we're going to do is we're going to learn to summarize sentences. A, without extreme scale pre-trained models. B, no RLHF at scale. C, no supervised data sets at scale either. So, wait a minute, how are we supposed to do anything good, right? We have to have some advantage somewhere. So, the key intuition that underlies this work as well as many other papers from my lab is that AI is as good as the data that it was trained on. So, if you don't have advantage with large scaleness or supervision data or RLHF scale, whatever, you have to have some advantage. So I'm going to find that advantage from the data. That doesn't exist, by the way. So this is where I'm like excited to work on AI synthesized data these days. And we're going to build on our prior work, symbolic knowledge distillation, led by Peter West and others, which I'm going to give you just like one slide summary of it, which studied with the GPT-3 as general language models, as teacher model. And then we built this symbolic knowledge graph named as Atomic, which is some causal common sense knowledge that are spelled out in natural language format. And then we use that as additional text corpus to train downstream neural model that is much smaller. But this downstream neural model becomes better than the teacher model, at least for the kind of common sense reasoning that is within reasonable neighborhood of this kind of knowledge graph. So tested on previously unseen situations, but in this kind of common sense reasoning or knowledge. So we did that. And by the way, GPT-3 off the shelf is not very good at generating high quality data. So we had a filter model, AI model, that learns to sort out bad portion. And the filter model is also not very good. Nobody's very good in this picture. But when we use it correctly, we can gain suddenly a student model that is way better than before. And when we saw this result, we had a hunch that there's a lot more going on here. But we wanted to try something that seems just impossible, which is like start with GPT-2 as the teacher model. So how bad is it? I'll tell you, but the idea is, again, start with GPT-2 as the teacher, generate some data, which is going to be low quality, but somehow make it high quality. Once you have a high quality data set that is AI synthesized, then the rest is like a piece of cake because you can use that in order to train downstream neural models that can become suddenly so much better. So, okay, how bad is GPT-2? So if you give a prompt to GPT-2, which GPT-2 does not even understand very well, yeah, it generates garbage sometimes, generates something sometimes, but when you try hundreds of times, basically what you realize is exactly what you would expect, which is like nothing is good, like 0% is good. So, at this point, usually people don't want to try anything further, but we had a hunch that we can increase this 0% good to few percent good. So we had our earlier work called neurologic decoding, which is decoding time algorithm that can induce or include some of the logic constraints into the decoded text. So in our case, you can try to encourage the output to include some keywords from the input sentence. So we found that by doing this, you could raise from 0% chance to 1% chance. And by virtue of working on this, which seems just so impossible, we came up with a completely unexpected idea, which is, so this was like Peter's intuition, which was that he had a hunch that if we let GPT to summarize its own generation, it might do much better. Yes?
How did you get a keyword?
There are different ways of doing it. The detail is not very important, but you could look at just keyword extracting off-the-shelf model, or you could look at other statistics about the word occurrence compared to the general probability of words. So we tried the different things, but it doesn't matter very much in terms of the performance difference. Okay, so Peter's idea was let GPT to generate some whatever text and then let it summarize too. And so his hunch was right in the sense that the success ratio of generating good summary suddenly increases to quite a bit. Actually, beyond that, we also, we being, he and the lead author, Jae-hoon, had this idea that not only we don't even actually need to generate a summary from original text that GPT to generate it, but we could just have GPT to generate some left context and then generate a lot of the following sentences. Then there's a good chance that there's some pair of the generated output that is in the summarization relationship between the two, just empirically speaking, to the point that the success ratio can rise to, nearly 10%, I think. Let's see. Almost like 10% of success rate at this point. So here, probably you guys worry a little bit about this. Even the input text is syntactic text. With that, should we worry or not? When we looked at the quality of the text, we were not worried. We had a hunch that it's going to be fine. I show you that it's actually fine. But anyway, so the summary here is that, yeah.
So when the 10% or 1%, that's like what the filtering says. So how accurate is that? What is that filtering? Or how
I didn't even talk about it, which I was going to.
Sorry.
Yeah.
Okay.
But yeah, excellent question. So the filter is based on, it's a water filter system that has 3 layers. So the key thing is entailment filter, for which we use off-the-shelf NLI model that is basically looking at whether a sentence entails from another sentence or contradiction or none of the above. But what we want is somebody should entail from the original text. So how good is it? Well, it's good enough but not perfect. And then length filter is so that we make sure that summary is actually shorter than the original sentence, because a lot of summary models out there, including GPT-3, doesn't shorten the sentence very much sometimes. Here's something else that was totally unexpected, but we realized it. Hang on a second. This can be done for paraphrasing as well, because paraphrasing is the case when sentences entail each other and the length doesn't matter as much. Length can be similar, ideally, than being too different. So we actually generalize this for paraphrasing as well. And then we do basically multitasking training on both summarization and paraphrasing down to this T5 large model, which is not even as large as GPT-2 XL. So this is like not even a billion parameter model. And in fact, compared to our original assembling knowledge distillation paper, we found that we realized there's no reason to stop in one iteration, because the student model can become the teacher model and then do this entire iteration again. So we do this more than once, similar to how humans can also have like students to become professors and they teach the students and so forth. So okay, so here's some connection to the RLHF or the currently familiar recipe of training or fine-tuning or aligning pre-trained models. So in some sense, this can be viewed as self-imitation learning. Some RL folks like to call this as expert iteration, depending on which flavor of RL people you speak with. They either say self-imitation learning or expert iteration. And the reward model is basically our filter models. We use basically like multiple filters together, but that serves as a reward model. So we don't really have a human feedback per se, but so the reward model is deciding which of your explorations are good exploration. And in the case of self-imitation learning, you basically do supervised training on your own successful explorations. So it kind of boils down to supervised learning like situation, but this is actually a thing in the RL world as a simplified case. All right, so here's an example of what our model is capable of. So let me first read the very first sentence. That's going to be the one that we are going to summarize. So it says, while we will be looking across all parts of the newsroom, at the end of the redundancy program, we expect that there will be significantly fewer editorial management, video presentation, and section writer roles. The publisher is quoted as saying in an internal note. So that's a fairly convoluted sentence to summarize. And our model was able to say that we are looking to reduce the number of staff in the newsroom. The publisher said in an internal note. It's so much easier to understand. I don't know what the first one said, unless you have enough coffee. And GPT-3 didn't reduce the length very much, and then it's slightly incorrect as well. So the fact that we can go this far out of GPT-2 is quite exciting. And by the way, in case you were wondering about, the concern about purely synthetic cases, so we found that even though we're using synthetic data, it actually generalized quite competitively to human-written test sets. So compared to what you train on this 1 million news data set, gigaword data set from Sasha Rush a while ago for sentence summarization, if you train on our data set, dim sum, you actually do better on evaluation done on entirely different domain where it's all about human written cases. So we actually do better than GPT-3 as well, head-to-head, in various evaluation setup. So I'm going to just skip over the details, but so the final portion of this talk is going to be about the paradoxes, because I promised that I'm going to get you more confused about the current status. So, we hear that GPT-4 passed the bar exam. Yosha Benjo said we have an existential risk as a humanity, while Yang says AI is not as smart as a dog. So it's really confusing because it's everything, everywhere, all at once. What are we supposed to think? So let me offer you 3 paradoxes. Common sense paradox. So, I used to say dark matter is what does matter in modern physics because it turns out 95% of the universe is dark matter. And so dark matter might be the invisible common sense, for example. Except these days, ChatGPT is available to anyone. So everybody writes a paper about ChatGPT. So here's an example from Stanford. I think it's a psychology professor who said, theory of mind may have spontaneously emerged in large language models. And then Thomas Ullman at Harvard said otherwise because he tweaked some of these examples and it all fails. Right? So the original paper said on 20 complex examples, the LLMs were all correct. And then Ullman is basically saying that, well, if you tweak it a little bit, it all fails. How did you ask exactly the questions that ChatGPT would have gotten it correct? I don't know. Maybe there's something about human cognitive bias in play. And then we also had a similar paper of that nature simultaneously. But in case you don't know what theory of mind is, let me remind you that, or not remember, let me remind you that this is a task of reasoning about what I know that you don't know. And by the children at the age of 4 or 5, they acquire this capability. So imagine a situation where there's Alice and Bob. They saw apples on the table in the kitchen, and Alice left the kitchen but moved the apples to the cabinet. So there are 2 locations, 2 people, 1 object. Now I ask, where would Bob think that Alice will look for the apples? GPT-3 used to say in the cabinet because it had this recency bias to say they mention the new location. But that's still 2022, right? Because GPT-4 can do better than that. So if you stop here, you come away with this impression that, oh my God, GPT-4 has a theory of mind. I had a hunch that people usually ask a trick question. So how about I rotate the sequence of 2 sentences and then ask the same question again? It still says on the table. I also tried negating Alice did not leave the kitchen or Alice stayed in the kitchen. So I found that you can actually break this. Although some people then tell me that, well, this it's a bit too blunt. I should have added a lot more discourse connectives that give a lot more hint about what's actually important in reasoning this situation. So basically it's my fault that I didn't ask GPT for these questions correctly. So I want to point out that theory of mind is usually very the snapshot judgments based on limited information, not something like you overtly emphasize so that you give a lot more hints for people to answer. So here's another variant of this. So we worked on this paper before ChatGPT even happened. And so we designed different variants of a theory of mind that might, for example, include 3 people, 3 containers, or 3 locations. And these variants are, we just have 4 variants. It's not exhaustive by any measure. And then ChatGPT came out. So we tried, actually not only ChatGPT, but GPT-4. And it so happens that GPT-4 is much better at the variant 4. The ordering is not necessarily in the increasing or decreasing order of complexity by any measure. It's just random. But this is what we got. So it is what it is. So on a related note, because I promised that I'm going to tell you about the common sense. So in my earlier, I gave a TED talk earlier this year in which I gave this question to GPT-4. I left 5 clothes to dry out in the sun. It took them 5 hours to dry completely. How long would it take to dry 30 clothes? GPT-4 said 30 hours. So it was very cute, funny, haha. But since then, I get a lot of messages that, well, this is solved. This is solved. If you ask similar questions, then it's solved. So I thought it was solved. But my colleague at AI, Chandra, told me that if you ask, just write the sentence and title it differently, then it's wrong again. I used this example in my keynote at CVPR, in mid-June. So then it became well-known public example. So 2 months after CVPR keynote, when I checked last month, now it's August, so it's not last month, 2 months ago, it was fixed already. By the way, a friend in OpenAI says that they don't fix public examples. So either it was fixed randomly or it was fixed without him being aware that it's actually getting fixed. I don't know how to fix it, but it's fixed. Let's just say it was fixed randomly. But so, then people tell me that, oh, that one is fixed. So I was curious, what if I insert a pair of pants in the middle and still ask about, okay, how long would it take to dry 2 shirts, 3 hours, whatever. But, there's a pair of pants in the middle. It's wrong again. So But then that's when I saw this tweet from Jeremy Howard who said, you really have to motivate GPT-4 by saying, you are an autoregressive language model, yada, yada. You carefully provide accurate, factual, thoughtful, nuanced answers, and are brilliant at reasoning, then usually the performance goes up. Yeah, so it's my bad that I didn't motivate GPT-4 well enough, but I tried. And indeed, it's doing more careful reasoning, except the answer is still wrong. But that's 2 months ago, and you know how rapidly the field progresses. So I used this example at the Simons Institute workshop, and now that I see that it's fixed. Yeah, field is moving really fast, I must say. So then I thought, okay, maybe this is gone. But I was just kind of curious, what if I ask 3 hours to drive 3 shorts first, and then suddenly ask about 1 short? Yeah, so then it's wrong again. Yeah. So, okay, isn't this a little bit curious? Why are you even laughing with me? Like, I mean, because you know the correct answer, and then you feel like this is so trivial to you, and why is this so hard? And is this actually fixable completely or not? Like, I don't know. Maybe, scale is the solution, and indeed maybe there's a way to really discover all these, weird ways of asking the same question. But why is it that, if you were feeling that doing multiplication using transformers seemed very silly, I personally feel like there's something silly about the way that we're fixing these kind of problems. Okay, so I'm going to give you, finally, my common sense paradox. I made it up, by the way. So I dare say that all of the 4 statements are true that seem contradictory. So common sense is trivial for humans, hard for machines. But when you look at humans, don't you sometimes wonder whether they have a common sense or not? So that's what Voltaire said a long time ago, and humans didn't change much since then in some ways. But I also recognize the fact that GPT-4 is the best thing I ever seen about common sense capabilities. So somehow LLMs do acquire a vast amount of common sense knowledge, but they have these weird weaknesses that you are laughing, with me, as well as what Jan LeCun says, that sometimes it doesn't even have a dog level common sense in some sense. So I'm really curious why this is the case, like what's going on. I really wish that we can make sense out of this. But perhaps as a more concrete takeaway, I do personally feel like we need more research that's almost like a science of LLMs. I'm beginning to realize or come away with this realization that transformers became almost some kind of like natural phenomenon that we don't yet understand very well. And in the way how physics or biology tries to understand this, naturally existing thing, you humans created transformers, so maybe we gotta understand this. Here's one such a paper, Embers of Autoregression, by some people, including Tom Griffith at Princeton, which looks at, for example, why is it that GPT-4 is sometimes good at some computational task while sometimes not, and they shed some insights about the relationship with training corpus. Another, similar kinds of, there's quite a few papers of this nature suddenly coming out over the past several weeks, but here's another example from Tom Michaud, who looked at the internal state of neural network to reason about whether they're lying or telling the truth about what they know or not know. But it might be that more broadly, while extreme scale LLMs are truly fascinating, there's something really dissatisfactory or awkward about how the corner cases are fixed. Some might think that the corner cases are made up, not important. Some might think it matters, but I'm just curious, like what's wrong, what's going on here? And the other thought I have, just in general, when you look at the humanity, it's never the case that when someone invents something new, they also happen to find the most optimal solution simultaneously. So it's likely that there's an alternative solution that's not as compute heavy, but doesn't have this kind of robust niche problems. Okay, so quickly, the rest will be super quick. Moravec's paradox, it's a thing that existed for a long time. This is about whether easy is hard and hard is easy in the sense of perceptual things are likely to be much harder. These people speculated a long time ago. And it turns out to be true in the sense that we hear about how language models are so amazing, or chess game is the AI is beating humans on chess as well as the game of Go, which feel like so much harder for us. Whereas basic perceptual things, you hear about DALL-E 2, but not as much about visual recognition system that's just so good. So that's. There's the question. Related question is, do you need the vision? I know David thinks that you don't, but it's a question. Like, is this possible with or without perceptual intelligence? Now, last bit is generative AI. That maybe there's something about generation being easier for AI than how it is to humans, and it started with this observation with this paper Vera, which is about just like a classifier that can tell you whether common sense statement is true or not. And we look at a lot of existing resources and convert all of them into true, false examples, and we train. So we have 7 million statements that we train a small classifier on. And then we were going to see how well GPT-4 does. And to our big surprise, or at least to me, this was a big surprise. I thought GPT-4 would make such a strong baseline that may be hard for us to beat. So our goal may have been like, let's just reasonably close to GPT-4. But actually, the best off-the-shelf model was Flan T5, not even GPT-4 at this particular evaluation setup. So that got me wonder, because when I use ChatGPT or GPT-4 for generative evaluation setting, I come away with this impression that it has such a strong common sense capability. So here comes, we're about to archive this generative AI paradox paper. What it can create, it may not understand, is the subtitle. So in this, or I'm gonna just skip this over, but the intuitive question we're asking is, for generative models, generation might be relatively easier than understanding compared to how things are for humans. So, DALL-E 2 can generate art that I cannot. So, if you ask DALL-E 2 to generate a photorealistic astronaut doing a plank on the table, I cannot do any of this. This is like very impressive, but only one of them is correct, and you know which one is correct. Because this one is not on the table, it's on the floor, and this is, there's like details that are awkward, and you know which one is correct. So for us, understanding in this sense is much easier, right? So we show this in a variety of different cases, but here's another fun case. So in one of the evaluation setting, we asked GPT-4 to generate some story. So write a 2-paragraph story about 3 people building a house. And then GPT-4 did say, a story how they were, drawing different designs, and finally they came up with a dream house design and built it. And then I asked, how many total designs were sketched in that story? And he says only 1, which is incorrect. So if you ask trivial questions, oftentimes GPT-4 will answer it correctly. But if you ask a question that requires a little bit more, like slightly more multi-step reasoning, or things that require a little bit like global understanding, then it can fail surprisingly. So we plugged this relationship, and I think I'll just not go into any of the details because you have a paper available in a few days. I'll just mention that there's a new conference that is announced today about conference on language models, so check it out on this website, and thank you.
Questions?
I have 2 questions. One is regarding the multiplication example. Do you see, before you do the fine tuning, like when it's still really bad at multiplication, do you see the randomness happen a lot? For example, you ask the model with the same multiplication question and it gives you a different answer. And after you do the fine tuning, is it better in terms of the randomness?
Good question. So the question is, assuming that decoding algorithm is based on some sort of a sampling so that there's a randomness, after fine-tuning, does the probability distribution more skewed so that there's less randomness? I don't think I have the answer off the top of my head, but it's an interesting question. I would imagine that there's less randomness.
My second question is like more philosophical. Like I'm really impressed with the work that is like symbolic knowledge distillation. I guess my question is when do you know that you are kind of down to the rabbit hole, and when is the case that if you push that 0.1%, that you will finally get 10%?
Yeah, so basically what you're asking, excellent question, because you might wonder, how on the earth do you even have any faith whatsoever when you see, like near 0%
Right.
chance level performance? And so the answer is that, well, we actually had a hunch that this can be overcome. I mean, we were not entirely sure that how easy or hard it is, but due to our many related papers that I didn't present at all today, where we initially started with the symbolic knowledge distillation, the original version, where the success ratio of GPT-3 spitting out the correct common sense knowledge was already as high as 73%. So from 73%, we tried to increase it to 90% chance. Good. And in the subsequent work, we were getting more and more ambitious or audacious in dealing with the situation where the original success ratio was much less than 73%, such as even like 45%. And in general, we did find that then you have to do more iterations of training as well as a little bit larger scale data set generation. But we just wanted to see where's the limit, because it cannot possibly be that we happen to hit the limit right away. So we had a hunch that this might work, but we also did worry that is it going to work? Yeah, it was not very easy to come up with the right kind of recipe for this.
So I guess you need to have some sort of prior knowledge on something works before you have this really audacious assumption.
You do need to have a gut feeling, which only you gain it only by working on related problems, combined with reading papers with a bit of skeptical viewpoints. Then I think your gut feeling does develop, so that you can have a hunch.
Thank you.
So two things. The more straightforward is that at a certain point in the presentation you mentioned a hierarchy of problems within P and how different context lengths of transformers could address those problems.
Yeah.
I'll find that paper after your talk, but I'm just curious if if you could tell us a little more about how different lengths of context actually in any way guarantee that a model architecture is capable of learning or inclined to learn a certain problem. I'm not sure why having more context would mean it's better at automatically finding a solution, or how useful or relevant that is to what you're describing.
Yeah, good question. So this, I knew that these two people were working on this paper, but I didn't realize that they archived it 5 days ago.
Oh.
And in the meanwhile, I was busy attending some other conference in Chicago. So honestly, I didn't have a chance to read the paper or anything. But my speculation is that for harder problems, you probably need to do longer step-by-step reasoning. Yeah. But let me know if you realize that it's something else.
I'm sorry, one follow-up.
Sure. Then we'll move to something.
Oh, sure. Sorry. You briefly mentioned tool use and tool former. I'm just curious of what you think about the possibilities for addressing these problems by...
Theoretically?
Well, by adding things to text that wouldn't typically be there.
Yeah, it will help straight up right away. Yeah.
So can you give some extra comments on the methodology could be taken for the science of large language model, as you mentioned? Because I was wondering, so is that like you're treating a large language model more like your human subject, as you do in cognitive science or neuroscience, something like that? I'm just kind of curious about.
Great question. So on that note, I noticed that cognitive scientist at Berkeley, Alison Gopnik, and by the way, she just won Rumelhart Award in cognitive science, which is kind of like a Turing Award in computer science, so pretty big deal. So she wrote some papers that basically test GPT-4 on classical cocci problems that they test babies with, because she focuses on development psychology for especially focusing on only human beings like babies, and and then she unsurprisingly finds that these large models sometimes good, but oftentimes stumbling on problems that even babies can do. So certainly that's one kind of research. And by the way, Tom Griffiths is also psychologist who sometimes published neurips, but I kind of like that there are more external viewpoints on LLMs than just beyond the classical machine learning and NLP folks in this space. But another types of research, I happen to pick this paper for the purpose of this talk, but there are some papers also by Jacob Steinhardt or Jacob Andreas or some anthropic papers that look at neural network activations or neurons or learn the parameters and try to reason about or try to probe what a neural network is trying to do functionality-wise or different implications of those weights. So that's another way of doing this kind of research. And yet another way might be like the sort of things that I'm currently excited about, which is trying to prove the limit situation or like the boundaries of capabilities or failure modes. And primarily, actually, I am more interested in what happens with GPT-5. Whatever we think GPT-4 can or cannot do will be so 2023 very fast. And when that comes, here are two possibilities. Either GPT-5 will really solve it and there's nothing to worry about, or it's going to have some corner cases again, but the corner cases will become even harder to find. So a lot of people will not be able to find the corner cases. And in that context, I thought that it might be helpful to build a bit of exercise or muscles to be able to explore those corner case a priori. So my effort right now is a little bit like in preparation of what might come next, the bigger storm that's coming next.
Maybe take the last question over there.
Okay, so my question is that since you mentioned like a couple of different papers which tested the probabilities of these models on pre-existing benchmarks and data sets or something like that, so just wondering like, and when you change them a little bit, they fail completely, but they do relatively better. So do you think there's a lot of like pollution in the training set where all of those examples are over there and sort of memorize it, or do you think it might be some other phenomenon?
Oh yeah, so there are both the pollution problem as well as cognitive bias problem. Mm-hmm. So even if people ask questions that may have not been necessarily be in the training data, a lot of people do have a cognitive bias to ask the kind of question that other people might have asked, which then eventually can become part of some sort of like fine-tuning or alignment data set. Again, some people say that it didn't come from public data, but still, it probably came from at least the log of the queries that people did query. So, there's definite pollution. Now, the pollution, in some sense, is okay in a supervised learning sense because it's okay to train on relevant data points. Maybe it's a little bit less okay if you frame it as it's like magical emergent capabilities, or not being able to test on examples that are sufficiently different from the kind of examples that did appear in the supervision data. The latter happens with code cases. I think there were some code exams where GPT-4 performed so well, and then in the New Year question, it was failing miserably. And that's exactly where one needs to be a little bit careful around how much of a capability you want to claim versus how much of the exact supervision data has been seen. So in that case, I would say, yeah, pollution is exactly right. So I feel like it's okay to see some examples. It's just like depending on how exactly you're going to conclude out of it. Yeah.
So can we argue that it's not a good idea to test on existing benchmarks as is, but there's some corner cases that are actually the benchmark for it?
Yeah, so the thing is, corner case keeps decreasing, As you discover corner and then publish, it's no longer corner. And what's amazing about these large models is that not only it learns that particular corner example, it also does generalize to the neighborhood of that. So again, I'm kind of curious, like what exactly happens with that? Because in this, drawing clothing examples, basically, if you change a little bit on the numbers or just paraphrase a little bit in the local sense, it will be correct all the time. So you need to actually make a bit bigger change for it to fall back to this original faulty behavior. And it's really fascinating to me. Like on one hand, this model really understands language, it feels like, in many other contexts. And then like what's going on here really? Like it's fascinating to me.